Let's start with what has now become your favorite image. You know all about it, and you know how many numbers you need if you want to describe most of the variance or most of the information in this image. So yesterday, towards the end of the lecture, we talked about textures or different realizations of stochastic processes, and this is one example that I used. And so now I'm going to ask you the same question. How many numbers do you need to describe this image? How would you even think about this? Okay, so let me remind you, in this image we have millions of pixels, and our quick estimate yesterday showed us that if we have about 1,000 galaxies, we will need about 20,000 numbers to describe what we see with some precision. And how can we apply, a similar approach to the image on the right? All right. Sure. To reproduce this with much fewer numbers than the number of pixels in this image. As close as possible, yes, yes. So that's one possibility to describe this image. And now there is a second question, which is my next slide. Okay. Now, those are different realizations of a process. And when I show you this image, one question could be to characterize this exact image, or can I try to learn from this image and try to basically generate images that will look like it? Okay, so the same texture, but different realizations. Okay, so how could we do that? All right, that's what we are going to explore today. And so this is really the core of the challenge for image classification. Okay, so when we want to classify different images, when you look at this, your brain does that in a fraction of a second. But the question is, how does that work? What happens during that process? Okay. And so what allows you to characterize those different patterns and different categories, and how would you write a code that does that? Okay, so that is the challenge of image classification. Those are images from the complex world around us. They are even more complex than the ones we saw before with astronomical examples, but the challenge is the same. Okay, so we know it's possible because, our brain does it. And in addition, we now know that deep convolutional neural nets can do that too. Okay. But there are lots of questions that come with this. Okay, so how do these neural nets do that? Why do we need convolutions? What kind of filters do we need to use? How many layers do we want to have? Why do we need nonlinearities? Why do we need pooling, et cetera, et cetera? Okay, so those are all the operations that are being used in these nets. But the questions now are, why do we need this kind of architecture? And if we understand, perhaps we will be able to use this knowledge to optimize the architecture that we want to build. All right. So when we do this, and when we do machine learning in general, we are basically doing just one thing. We are trying to approximate functions. Okay, machine learning is just function approximation. So what is function approximation? Okay, so we have a very complex function f of x here, which could be, from a mathematical point of view, continuous. And we want to approximate this function with a finite expansion. Okay, so n is going to be the order of the expansion, and we want this to be as small as possible. And we want to approximate this function with some accuracy, or within some accuracy. All right, that's the challenge. So we know of different techniques to do that. We can use various expansions that you are probably familiar with, the Fourier transform. We can use polynomials or even orthogonal polynomials if we like. Okay, so those are techniques that will allow us to take any function and approximate it with a finite series up to some accuracy. Okay, so we can try to use these estimators and see whether they are going to be useful for us or not. Some of you might have heard that there is out there a universal approximation theorem, which tells us that we can actually approximate any function. You can read all the details later, but the idea is that we can approximate any function using this kind of expansion. Okay, and so what we have here, we have a finite expansion where we have a series of some amplitudes, phi, which is a nonlinear function, and then we have some weights applied to some variable x and an offset. Right? And you might recognize here the architecture of neural nets that is showing up. So this is nice, but this theorem doesn't tell us very much. So it tells us that if we use a feed-forward network, we can, with a single hidden layer, so the condition here is to have one hidden layer at least, and so with only one single layer, one can approximate any continuous function. Okay, so it's good to know that this is possible, but the theorem doesn't tell us anything about how to do this in practice. Okay. It doesn't tell us about how many parameters, or what is n that we need here, and how to learn all these parameters that are stored in this weights w here. Okay, so we'll have to do that ourselves. Okay, so if we want to do classification, we have to capture similarities for objects that are within one category and the dissimilarities for objects that are in different categories. So how to do this? Okay, can we do image difference to compare different images here and to know whether they are close or not? Okay, no, that's not going to work. Can we look at color histograms? It's not going to take us very far. Or brightness histograms, that's the same limitation. Okay, so we have to deal with lots of objects of different shapes, sizes, orientations, etc., and specificities. Okay. So perhaps these objects are located on some low-dimensional manifold. Okay, this is what we discussed yesterday with dimensionality reduction techniques. But what do you think? I mean, are these pictures of cats distributed in a low-dimensional manifold or not? Okay, so they are not. So first, the space is huge. We have images with, let's say, 1 million pixels or more. And in that space, these objects are not going to be distributed as smoothly as we might like them to be. Okay, so there is a real challenge there. So the challenge for us is to basically find a metric that's going to be informative. So we have data objects. I'm going to call them X. They live in a very high dimensional space. What we want is to estimate distances between objects, distances between images. We know that a simple difference, or the norm of the difference, is not going to be informative, so we have to come up with something else. And so we need to create a metric which will be such that when two objects are of the same category, there will be a small distance between them. And when they are not, the distance will be large if they belong to different categories or classes. So we need to basically do a change of variable. Okay, and so we need to find a new representation, and I'm going to call that phi, such that if I take two different objects, and that belong to the same class, the distance between these objects using this representation is going to be small. Okay, and graphically, this is how this looks. This is the data space, which is in many dimensions, millions of dimensions. We have different images. I have two categories here, blue and red. If I pick a point X here, this is a new image that I have, I want to know whether it belongs to the blue category or the red category. And so my challenge here is to come up with a new representation of the data that's going to transform this distribution of points in something that will look like this, where it will be much easier and where I can use simple linear classifiers to know whether X belongs to the blue or the red population. Okay. So now the question is, which properties are required for this function, for this representation phi? Okay. So this is not easy at all, and it took people many years to come up with something reasonable here. We have quite some challenges. So first, we work with many dimensions, millions. The signals we are after, they are not nicely distributed along some low-dimensional and smooth manifolds. It's much more complex. It's something like this. Okay. We have usually a very limited number of training examples. Okay, the number of images that we have to learn this representation is much, much smaller than the number of pixels or the dimension of the space. And as a result of this, we cannot use interpolation. Okay, interpolation here would be meaningless. Okay, and for it to be meaningful here, I would need a huge number of training examples. Okay, a number that would grow exponentially with the number of pixels. So this is completely out of question. Okay, so I cannot use interpolation to do that. I cannot make use of direct neighbors in a space like this. So what can we do? So we need more information. Basically, we are starving for information here. Okay, our data is too limited. So one way to do that, and that's basically what your brain does without you noticing, is to make use of symmetries. Okay, and this is also what we do in physics when we solve problems. Okay, so we are going to try to make use of as many symmetries as possible to try to come up with a representation, okay, that using this symmetry will allow us to go from here to there. All right, so now it's going to be your turn, okay? The challenge is to try to define this representation and its properties. So I'm going to ask you, and you are going to do that with your neighbor, as usual, to give me the lists. So if we want to come up with a wish list for the properties of this representation and all the symmetries that it should have, can you please tell me what this list should be? So I'm going to give you a few minutes. Think about it. We want to think of all the possible symmetries and invariants that this representation should have with it. Go ahead. Say it again?
Invariance to background.
That's a good one, yes. I have 6 items on my list, plus an extra one if people really want to push.
I have 5. Background's a tough.
Oh, yeah, you're missing one, yeah. I mean,
Invariance to color, I don't know. This is kind of a boring one.
flipping, if you have rotation and translation. Oh, you mean
No, I mean
mirror symmetry?
put it upside down. Although upside
But it's a rotation. I think even this is a rotation too, right? I see what you mean, but that's. All right, I have 6 items on my list. I hope you are reaching a similar number. You can continue to, if you haven't reached 5 or 6, you try to get there. How many do you have? Okay, so let's see. What kind of properties do we want for the representation? Okay, so we basically want some invariance. Okay, what invariance would you like to have? Someone should start. Yes. Okay. So invariant, let's do translation. Okay. Another one. Rotation. Okay. Parity. Okay. What do you mean by parity? Okay, I'm going to put it together with rotation. They have a similar flavor, right? Okay, what else? Color, invariant to color. Okay, so let's finish. Let's come back to this in a second. Let's finish with the spatial transformations. I heard scaling. Okay. What else? Sorry? We have rotation here. It doesn't have to apply to the entire image. Okay, it can be local. Yeah, let's put that into parity, yes.
Like the object doesn't have to be like an entire cat for it to be a cat. It could be like only face.
So that's not an invariant. It's something that's a little bit different, but you are touching on an interesting point here, is that actually when we think we see cats here, okay, what we are really seeing, we are seeing catness, okay, really. Because you can see half a cat. Okay, half a cat is not a cat. You can have occlusions, and you can have all sorts of distortions. Okay, you will still recognize a cat. Okay, so basically what those things are, it's like going back to texture a bit if you want. Okay, what we are seeing is catness and rabbitness. Okay, so we don't need to see the entire object to recognize it. Okay, so we heard something about colors. Okay, so let's simplify things a little bit here. Let's just talk about brightness in general. And of course, brightness can be as a function of wavelengths. But we want to be invariant to brightness transformations. Okay.
General numbers of something, that's invariant. Something has 4 appendages, it stays 4 differently. Does that count?
Sure, so I'm going to say that basically what you want is to be stable. Okay, so if like a fraction of the object is not visible, you can still detect or recognize it. Is that what you mean?
No, I mean that, for example, something 6 spheres is not a sphere.
Oh, okay, but that's fine. If you can detect one, then you can detect many. If I understand what you mean.
For example, there are angles between those two. I don't know what you call that. It's not invariant. Some relationship of distance, internal distances between
So those are some of the features that we want to use. That's right.
So the invariance, that's what you use for.
That's what we use. But the thing is that these features are not always exactly the same.
Right.
So we want to be invariant to something here. What is that something?
Proportions and scaling.
Scaling is overall scaling. Okay.
Perspective is the
Prospective, orientation,
like that something is
yes. So that's going to be captured by some of this, right? But now when we recognize a cat, it's not always the same cat, right? So what I can do, I can basically add some small deformations, and it will still be a cat, okay? But if the deformations now become huge, you will no longer recognize the cat. Yes? So basically, we also want to be invariant to small deformations. What else? So that's going to be included in the small deformations, right? Yes? The background, yes. Okay. So we don't want to be sensitive to the background. Okay, and the background can be, you can just, as the most simple model, it could be just a constant. You don't want to be sensitive to that additive constant. Of course, you can make it more complex than just a constant background, but you don't want this to affect your ability to classify. Anything else?
Could I ask whether your small deformations include small blockages, fractional?
Yes, so
Overlapping things, for example, multi-horses do not. You don't see the whole horse each time.
yeah, so you want to be stable.
Loss of parts of the object that would be. It's a deformation at some level.
At some level, it's a deformation, exactly. You can occlude or deform a fraction of the image. Yes. Yes, and you want to be robust to noise, exactly. Yeah. Okay. Anything else? I'm running out of space, so yes.
Sampling, if you have the same image with a different number of pixels, you should be able to recognize the image down to such.
That's right. So I'm going to include that in scaling, in a sense. I know it's a little bit different. It's about resolution.
Well, I mean, it's how much information is in the image.
That's right. Yes. I completely agree with you. But let's say for one given data set, okay, those are the properties that you, but I completely agree with you, of course. Yes. At some level, it has to do with scaling. Okay, so let's see what list I have for you. All right. Very similar. We want to be invariant to translations, rotation, and scaling. Indeed. Small deformations. Okay. So you are scientists. Okay. So you can probably think of ways to be invariant to translation, rotation, and scaling. Okay. Mathematically, you might be able to start thinking of possible equations. But this one is definitely not trivial, right? Small deformations. Okay, that's a real challenge, right? I'm going to define small soon, yes. But intuitively, you agree with me that if I deform an object a little bit, you can still recognize it, but then there is a regime beyond which it's unrecognizable. All right, so ideally, we would like our representation to have all these invariants built in. Okay. So let's try to do that. To make it a bit simpler, first, let's not look at objects like this because they are really very complex. Let's simplify a little bit and go back to the world of textures and fields. Okay, that's also a bit closer to physics. So same question and same answer for these fields. Okay, and you agree with me that if I take a quarter of one of these images and I compare it to another quarter, then basically the changes are described by this list. Okay, that's what allows me to say that those two different regions are from the same process. Okay, so let's start with translation. How can we be invariant to translation? Do you know of an estimator that is invariant to translation? can I apply an operation to an image and obtain a statistical estimate that is invariant to translation? There is one that is very often used in astronomy, because often we don't care about the exact location of galaxies, for example, but on average, we know that they are clustered. Okay, I can measure the clustering of galaxies here in the sky or here in the sky, and I will get roughly the same answer. Okay, that is invariance to translation. Okay, and so this is something that I can obtain by using correlation functions, or if I stop at the second order, the power spectrum. So if I take some fields like this, I can try to classify them, or to extract information about them using a power spectrum. Okay, and the power spectrum is invariant to translation. All right. So that sounds good, but I can measure the power spectrum from each image, and then I can try to reconstruct an image using the power spectrum that I have measured. And if I do this, this is what I get. Okay. So for each image, this is a reconstruction which has the same power spectrum. Okay, so that's all the information that I extracted here. And I regenerate a realization, and this is what I get. You will probably agree with me to say that we have lost a lot of information. A lot of information has not made it to this representation. Okay, this is translational invariant. That's good, but we have not captured enough information. Okay, so that's one issue of the power spectrum. Okay, and the problem is that this is only a second order description of the image. Okay, and so it doesn't capture anything that is at higher order, non-Gaussianities, for example. So this is not enough. So you might say, okay, what about using higher order expansions? Okay, so I can include information from the 3-point function, the 4-point function, etc., beyond the power spectrum. So that's possible, but unfortunately, the variance of these higher order moments keeps increasing. Okay, so I can try to measure higher order moments from my images there, but the error, the noise, or the variance on these estimates will keep growing as I go to higher and higher order moments. Okay, so this is not stable. It's going to be very sensitive to outliers. So if I have like a few hotspots in my image, all my higher order moments are going to explode. Okay, so this is not a very good approach for what we want. Before going to the next step, I'm going to have a small parenthesis and tell you how to create those images. Okay, how can I take an image, extract the power spectrum, and recreate a new image? Do you know how to do this? Some do, some don't, so I'll explain this briefly. So the way this works, we can start with an original image. We take the Fourier transform of the image. We are going to get a complex image. And so this is denoted by delta in Fourier space. We can decompose this into amplitudes and phases. Okay, and so I will have an image for my amplitudes and an image in Fourier space for my phases. Now I can play with these quantities in Fourier space. Okay, so for example, if I set all the amplitudes to 1 and then I Fourier transform back, this is the image that I'm going to get. Okay, so here I have kept the morphology of the image. You can recognize all the filaments, but I have lost all the power, all the fluctuations on larger scales. Okay, and similarly, what I can do, I go back to the Fourier space here, and I can keep the amplitudes. So I keep the power spectrum. The power spectrum is simply the second order moments of the amplitudes in Fourier space. And I can randomize the phases. I do this, I Fourier transform back to configuration space, and then I get this image. So this image has the same power spectrum as the original one here. Okay, but we have destroyed all the morphological information. Okay, so this is how that works. You can do that with a few lines of code. All right, I'll show you another example. Do you recognize who that is? Please. This is Planck. Okay. What about this one? This is Planck too. I can play with these images. I can go to Fourier space. I can extract the amplitude from the top image and the phases from the one at the bottom. And I can oops, did I invert the, yes, I did invert. Sorry. So this image, okay, I flipped my two axes here. So what I'm doing here, I'm extracting the phases, I'm sorry, from this. I'm going to correct that right now. Okay. And the amplitude at the bottom. Sorry about that. All right. Okay. All right, so I get the phases, so I have the morphology, and I extract the Fourier amplitude from this one. So I can reconstruct an image at the end which has the same power spectrum as the satellite, okay, but it has the morphology of the scientists. Okay, so you can play with these operations in Fourier space. Good, that was just a parenthesis. Let's go back to what we really want to do during this lecture. So what we want is to find this representation that will allow us to take an image like this, make use of symmetries, and come up with a representation that will be informative about the field. Informative in the sense that we can use it to classify different fields. So to do that, I'm going to show you a very wonderful tool. It's called the wavelet scattering transform. This has been developed by mathematicians over the past 8 years or so, by Stefan Mahler and Johan Brunner. And so in the following, I'm going to use many of their figures and their slides to show you how this works. So this is not my work, it's their work, but I think it's fascinating and extremely powerful. All right. So we've seen that the power spectrum does not extract enough information. So let's try to use something else. Let's try the Fourier transform. Okay, so we know that with a Fourier transform, so first we know it's translational invariant. I take a Fourier transform, I take the modulus, I can translate the original image, the modulus doesn't change. Okay, so I have my invariance to translation, that's great. If I want more information, I can expand the series. And I know that I will add more information. It's not going to blow up the same way it blows up with higher order moments. So this is good. Now what about the robustness to small distortions? Okay. So what we want here is a metric that is stable to deformations, to small deformations. Okay. So what does that mean? It means that if we do small deformations in the image space, our representation will change only by a small amount. Okay. So basically what we want is to capture this set of variations. Okay. The digit 4 here has been written in different ways that can be encoded by small deformations. You can still recognize it. And so what we want is, now I can introduce mathematically what I mean by small deformation. So I have my original data, x, and here I'm just considering one dimension, t, okay? Could be time in 2 dimensions, it could be spatial x and y variables. And I'm going to deform this, okay, by adding a term here, which is going to be my small deformation, okay? And so x with the subscript tau is the deformed data, all right? And so what I want is that if I take the gradient of the deformation here, the gradient of tau, I want that the maximum value of this gradient times the data, okay, is always going to be larger than a small change in my representation space, okay? So if I deform the data up to some value, I want to have a very small change of my representation. Okay, and this is characterized by the gradient of the deformation. All right. So how does that work if we use Fourier transform? Okay, so I forgot to say, this is basically now trying to encode warping. Okay, and if some of you have done gravitational lensing, you will also recognize that this is the same equation as what you get when you have a deflection angle, when you have light propagating. Okay, same formalism. And lensing will also create warping in the sky. All right. So this is what we want, okay? We want to be stable to small deformation. So let's introduce a small deformation here. So tau is going to be 1 plus epsilon, okay? So a small number times my variable t, okay? And I could do the same with x and y in space. So now let's look at what happens in Fourier space. So I have some data object x of t. I take the Fourier transform, I take the modulus, and I will get the blue curve here. Now I deform this object and I do the same operation, I get the red curve. So at low frequency, we see that the red and blue have not changed so much. But as we go to high frequency, then they don't overlap at all. Okay, which means that those two representations are very different. Okay, if I take a dot product between the red and blue, most of its coefficients here will be 0. Okay, or if I take the difference, I will have large numbers, meaning that the blue and red distributions are far apart. So what this is saying is that if I use Fourier expansion, I'm invariant to translations, that's good. But if I add a small deformation, okay, the low frequencies will be stable, but the high frequency components will diverge very quickly. Okay, so that is not good. Okay. So the Fourier transform is not what we want here. Okay. There's another approach, and that's the key idea of the scattering transform. We are going to use wavelets. Okay. So wavelets, in this case, we are in one dimension first. So we are going to introduce wavelets. So it's a complex object. We have a real and an imaginary part. Okay, it's just a simple fluctuation which we are going to use to extract information on one scale. The black curve here is the modulus, or the envelope of those two. And what is very nice here is that wavelets are localized. Okay, the problem with the Fourier transform is that the Fourier transform is too delocalized. And so when we inject a small deformation, we are going to change everything, all frequencies, and the high frequencies change very fast. So what we want is something that is more localized and less prone to these deformations at high frequencies. Okay, and because the wavelet is localized in space and frequency, it will have this property. Okay, so it's going to be stable to deformations. Okay, and in other words, what they do is that they are going to linearize warping. Okay, so if I take a wavelet and I deform it, I get a similar wavelet. Okay, the dot product between the two will be close to 1. So this wavelet is going to extract information only on one scale, okay, or one frequency. Now, if I want to extract all the information from my data, I will have to span the range of frequencies, and I'm going to extract information in different frequency band passes. Okay, so by doing this, I can extract all the information that I have in my data, and I can express it using this new representation. So what you see here is just, so my wavelet is psi on a given scale, lambda. And so I have a series of convolutions between the data and those wavelets to extract information as a function of scale lambda. And to extract all the information, I also need to extract what's happening at 0 frequency. And this is just a simple convolution, for example, with a Gaussian centered at 0. Okay, so by doing this, I extract all the information. I preserve the norm of the data. Okay, so it's a unitary operator. That's good. This is in 1D. In 2D, it's the same story. The only thing that changes, I need to use 2D wavelets. And so this is how they are going to look like. Now, our frequency space has 2 dimensions, W1, omega 1, omega 2. Same story. If I want to extract all the information, I need to basically scan the entire space of frequencies. Good. So now what can we do with these wavelets? Okay. So the good thing is that they are stable to deformation. But now the problem is that they are not they are not invariant to translation, because the wavelet is localized. And so if something moves with my data, that's not going to be good for this wavelet. Okay. So one way to come up with a representation that is going to be also invariant to translation is to use averaging. Okay. I don't want to average my wavelets directly, because on average, they oscillate around 0. So if I just take an average, I'm going to get 0. So what I want to do to extract the information, and I will not go into all the details, but what the mathematicians tell us to do is that there's actually one way to be stable to both additive background and deformation together with the translational invariance, is to take the absolute value, the modulus. Okay. The modulus will give you an envelope, okay? And then you average this over some scale. Okay, so by doing this, you are going to extract information on one scale, okay? And if we average between, here and here, basically I'm going to be locally invariant to translations within these two boundaries. All right, so I'm going to be locally translational invariant. And I have extracted information. So far so good. We have several of the properties that we want to have. Let me try to explain how this works. Let's look at the Fourier space first. So this is time, and this is frequency. So in this space, if we take a Fourier transform, we are going to basically sample the space like this, and it goes all the way to infinity. And as I showed before, if I have a small deformation, I'm going to expand this grid. And if I put some blue lines over the red lines and I dilate the blue ones, at high frequencies, they will no longer overlap. Now, if I use these wavelets, this is the representation that I have. Okay? So as I go to higher frequencies, I'm going to use wider band passes. And this is going to be stable now to this dilatation or deformation. Okay? So if I have some points here, and they are moving faster at higher frequencies, this wavelet representation allows me to preserve the invariance. Okay. The problem is that, so on one hand, wavelets are they are delocalized here, but they are very localized in time. Okay, so they are no longer translational invariant as the Fourier transform is. If I want to recover that translational invariance, I need to average over some scales. And within those scales, I will be locally translational invariant. Okay. Another way to show what the effect of the wavelets and the modulus do, this is the story we went over before for the Fourier transform. And now this is what you get if you use this wavelet transform and the modulus. Okay. What you see is that a small deformation now is stable at high frequency. Okay, there is much more overlap between the red and blue curve than before. So this is telling us that we are going to be stable to deformation. If we want to be translational invariant, we need to do some averaging. But if we do some averaging, we are losing the small scale information. Okay? So this is what is happening. So far, we have built an estimator that has some of the nice properties we want, but because of the averaging process, we are losing information. So we need to recover that information. One way to do that is actually to apply a second wavelet transform, okay, at a different frequency, or it will scan a range of frequencies. And by doing this, we are going to be able to recover some of the small scale or large scale information that was lost because of the averaging. Okay, because we are going to repeat this operation, it's going to have, again, all the properties that we want. It's going to be stable to deformation. It's going to be locally translational invariant. Okay, but now we are no longer losing information because we are going to recover this information on different scales each time. Okay, this is a representation that is very redundant. Okay, so many of the coefficients that are coming out of this will be redundant with some of the others. Okay, but it's going to be stable to many of the changes that we discussed. So now, this is a two-step process, but now I can start to iterate. Okay, I can do that many times to scan all the scales that I have in the data. And by doing this, what I end up having is a convolutional network. I start with my data, I apply the scattering transform the first time, and then I'm going to apply it again and again. And by doing this, I can extract all the information I have in my data. At each layer of this tree, I'm going to extract some coefficients. Okay. So this is different from the neural nets you are used to work with. They only give you one number at the end. This is going to output numbers at every layer. But what you can see here is that we are starting to see the architecture of a convolutional neural net emerging. Okay, so by requiring translational invariance, stable to small deformations, etc., the natural answer to this is to come up with a series of layered convolutions. Okay, and we know that this is going to extract the information and will have the desired properties. There is also a very interesting property that this is a contracting operator thanks to the absolute value, which means that as we go to higher orders, the coefficients do not blow up. Actually, they tend to zero because we are extracting all the energy from the data. Okay, so we know that this is going to converge, and there will be a layer at some point where the coefficients will be zero, we will have extracted all the information from the data. So that's a very nice property. So finally, at this stage, what we have is a representation of the data. So all these black circles here, they are numbers that we are getting from this transformation. And these numbers allow us to have a representation of the data. This representation is translational invariant, rotational invariant, affine invariant. And this is going to allow us to go from this space to that space. Okay. So a bit more math, but basically if we want to generalize this, now this is directly a slide from Stefan Mahler, we can think about different passes in this tree. Okay. We can apply this scattering transform layer after layer. We know that on average we are going to preserve all the energy, and so this is a list of properties that we end up with. We have an estimator that is contracting, so which means that as we go down here, we are going to extract all the information, and at some point the coefficients will be 0. There is no more information to extract. We are preserving the energy. We are stable to deformations. We are translational invariant. Yes, and that's already, a fair fraction of the list that we have on the board over there. Okay, so this is extremely interesting. Okay, it allows us to transform the data and to end up in a space that has all these very nice properties. All right, so we can do all sorts of things with it. This is an example. We start with some function. This is in 1D. We apply this cascade of convolutions. We obtain a list of coefficients. And because it has these nice properties of preserving all the energy, etc., we can actually invert the transform. And just from this, I can go back to the original data. And as you can see, all the information is there. Okay. Good. So now let's start to apply these two images. All right. I have two different textures here. And they have been constructed to have the same power spectrum. Okay. So what you see here is the 2D power spectrum for these images, and by construction, they are the same. Okay, so this is an example for which the power spectrum would not allow you to tell that there is a difference between these two. Now, if we apply this wavelet scattering transform, those are the coefficients that you get at the first order. And as you can see, they are similar. They are not exactly the same, but they are similar, which means that at first order, the scattering transform carries information that's similar to what the power spectrum has. Then we can go to higher order, and you can see here that then the coefficients are very different, and we can use this information to discriminate between these two different classes. Okay. The point to realize here is that the number of coefficients that we have here is much smaller than the number of pixels in the image. Okay, so we've been able to come up with representation that is much, much more compact, and that has all these very nice invariants built in. So once we have, this is an example for two images. Once we have this, we can do that for many examples. And so these people have applied this to texture recognition or texture classification. As you can see, so we have different types of textures here. You saw some of them yesterday. We can take each image. We can apply the scattering transform to extract the coefficients. Okay. Now, instead of being a space in a space of many millions of dimensions, we are only working with hundreds or perhaps a few thousand numbers. Okay, it might sound like a lot, but it is much, much smaller than the original space, the dimension of the space. And we know that these numbers, okay, so this information here has all these nice properties. Okay, so we know that if we apply this scattering transform to, let's say, for example, these different images, we will have coefficients that will be very close to each other in the space of representations. Okay, so that's a wonderful property. This can be used to do all sorts of things. This is the usual MNIST classification exercise. You can take an image like this. So what is being done here is that locally, in different parts of the image, one can apply this scattering transform to extract the coefficients. And in this space, one can basically classify coefficients in a very powerful way. This was done in 2012. And back then, in 2012, the scattering transform was the state-of-the-art classification technique for the MNIST dataset. Okay. And so what you see here is that using a standard convolutional neural net, this is the error that was obtained. And this is shown as a function of the training size. Okay, and you see that for all possible training sizes, the scattering transform performed better. Okay. One of the reasons also here is that the scattering transform does not need any training. Okay. It's a cascade of wavelets, so you don't have to train anything. It's ready to be used. You apply to the data, you get coefficients, and then you just do linear classification. Okay. All right. Let's talk about maximum entropy. If you remember what you can do with maximum entropy, given some constraints, you can define the distribution that maximizes the entropy, and you get the Boltzmann distribution here, and the key point to remember is that it's going to be exponential of the constraints. Okay? And the constraint is an expectation value of a random variable. All right? Now, if we have one image, we apply the scattering transform to it, you get a cascade of coefficients. Now, if this image is the realization of a stochastic field, okay, you can look at many different realizations. Okay? For each of them, you can apply the scattering transform. You will get one series of coefficients per image. And then what you can do, you can average, right? Here, the average is completely meaningful. Do you agree with me? Okay, so you have your list of coefficients, and this is just showing a scattering transform at the second order. So this is the image, first order, second order. You get a series of expectation values. Okay, this is similar to the usual mean and variance, etc. But now there are different estimators. And you just have to plug these estimators into the maximum entropy principle. And you get a distribution that can basically generate these fields for you, just using the coefficients. Okay? So that is very powerful. So here are some examples. We start with some images here. This is the size of the image, 60,000 pixels. That goes back to 2012. So we have different textures. As we saw before, we can measure the power spectrum of these textures, and we can use it to regenerate images, and this is what we get. Okay, and as you have seen before, a lot of the information has been lost. Now what we can do is to apply the scattering transform, and I believe this is only at the second order. We can use this maximum entropy principle, a Boltzmann distribution, and we can regenerate these textures. And now we are only using 600 coefficients. Okay, and this is much smaller than the number of pixels in the image. Okay, the number of pixels in the image can be arbitrarily large. Okay, so when you see these images, you know that you can actually represent them using only 600 numbers. Okay, and it works generically. It's not just restricted to one type of texture. It works for all these textures. Okay, so that was from 2012. These people have continued to work on this, and now they have very impressive results. So those are different simulations. Same thing. We have the original image, and we have the reconstructed image with the scattering transform. Okay, and this is using a few thousand coefficients. What you should appreciate here is that there is no training. Okay, we give just one image to the scattering transform. It extracts the coefficient, and we are done. We don't need to train over millions of images. Okay, this is one-shot learning. Okay, and so by extracting the coefficients once, we can then generate as many realizations as we want. And as you can see, it's pretty realistic. Okay, so a lot of the information has been extracted and used in a meaningful way.
What are you changing in the realizations?
Say it again?
Like what parameter are you changing in the realizations?
They are random phases. That's all. All right, so this takes us back to where we started. I discussed mostly about texture, but this can also apply to any images. Okay, and remember that when you see this, you are not seeing cats, you are seeing catness. Okay, an abstract concept of cat texture, if you want. And so when we want to classify images like this, or when we see them and our brain tells us what we are seeing, we are basically doing all these operations without realizing most of the time. Now what we've been able to do here is to start from this invariance. Okay, this is our wish list of invariants. And just starting from this, we've seen that we can come up with an estimator that can have all these properties. And one proposal for this estimator is this very interesting scattering transform. And so basically there's almost like, you know, there's a direct arrow that's going from the left to the right. If we want these properties, we must have filters that will extract fluctuations, and those are typically wavelets. The exact shape of the wavelet here does not matter. You just need a fluctuation that will extract information. We need to use an absolute value, and we need to use some averaging in order to be translational invariant. Okay. This might remind you of the pooling operation that is done in convolutional neural nets. We need to have a multi-layer architecture to extract information on all scales. And so this is very nice because we obtained all these properties just starting from the requirements here. Okay. At the end, this looks very much like a convolutional neural net. It's not exactly the same. Okay. The scattering transform will give you coefficients at every layer, but it has many of the qualitative properties that people ended up finding by optimizing over the years the architectures of neural nets. Okay. So now I hope you have a better idea of why you need convolutions, why you need to do pooling, why we need different layers, etc. Okay. Those reasons come from very basic requirements of symmetries. Interestingly, the filters that we find, the wavelets that we've used, that we have imposed on our scattering transform architecture are very similar to what people end up finding when they train CNNs. Okay, so this is those are Gabor filters, the wavelets we've used. This is the real part and the imaginary part. And this is showing the first layer of a deep convolutional neural net, which was trained with ImageNet. Okay, and as you might know now, these first layers typically go and turn into edge detectors. Okay, and so this is basically what we have directly with the scattering transform. All right. So to finish, I'm going to leave you with these images. The key point here is that depending on what you want to do and depending on the complexity of your image, you will want to find the best possible representation to extract information from the data. Okay. As we've seen, so we would approach this image and this image in very different ways. Okay. At the end of the day, they are not as complex as they might look. We saw that we need about 20,000 numbers if we have, you know, hundreds or thousands of galaxies. And in this case, we can also recreate images like this with thousands of numbers. Okay? Again, keeping in mind that we started with millions of pixels. So that's a huge dimensionality reduction. Okay? And the same type of operations, taking into account all the invariants we discussed, basically allow us to do classification with all these things. We talked about texture a lot. In addition to texture, here we also have sizes and shapes and so on, which I didn't discuss, but the ideas are similar. And I guess I'm going to leave you with this and take questions. Thank you. Yes. So people are using it as well. You can do one-shot learning with this. You cannot do one-shot learning as well with this. I mean, even a CNN would not. Okay. So what happens here is that when you have your different layers, okay. If you take a CNN and you look at the weights that you have at the end, as you know, so for the first layers, you will find these Gabor filters, okay, edge detection, edge detectors, etc. And as you go deeper and deeper into the net, you have more and more abstract concepts, okay? And so at the end, you end up with a space where you will have some filters that will look like, you know, someone's face or a car, etc. So what we can see here is that the first layers of these two architectures look very similar. But as we go deeper into the net, okay, the scattering transform will continue to have, you know, wavelets. It will not have someone's face appearing at a given layer, okay? And so if you go deeper into those nets, then you have different representations, okay? And then, of course, if you want to detect, you know, human faces, it will be very powerful to have a face as one of your filters, but the scattering transform will not have that, okay? And so some of the work that is being done now is to combine the usual scattering transform for the first layers and to have a slightly different architecture deeper into the network where you impose some sparsity and you use dictionaries to actually try to have filters that are better representations of the data instead of trying to represent everything. Okay, so those are the differences. Now, when it comes to texture, okay, so your ability to classify different textures mostly depends on the first layers. I mean, all the information, most of the information is going to be here. Okay. Yes?
Can you answer the question, how many parameters would be needed to define cats, for example, versus dog is more specific? Just roughly, what are we talking about? What images of, say,
Oh, so I don't have a quantitative answer for cat. I mean, it's also data set dependent. It depends on how many images you have and how many classes you have. So I don't have, I know, I don't have one answer. It's really data set dependent and resolution dependent and all sorts of things. And mostly, you know, how many different classes you have in your data. So I don't know.
But you're fighting for textures instead.
For textures, yes, you have the ability to say interesting things from hundreds to like thousands of coefficients. You are doing pretty well. Cats are there is more variability in cats than in just textures because you have shapes and positions and also, and the background, there is a background. With the field that I showed, there was no background basically. Yes? That's right. That's right. So it has to do with both depth and width. But so when you apply the wavelet filters, you have to choose how many different bandpasses you want to have. So there is a resolution there. What is done typically is to just use 2 to the power I, and you try to scan all the different frequencies you have just with this kind of tree, all the way to the smallest resolution you have in the image. Yes? The pictures, yes. Okay, so if you apply the transform to the entire image, and you have a limited number of layers, let's say if you just go to second order, which is not very deep, but that's most of the time what is used, or often what is used, for the entire image, it will not work very well. But what you can do is you can segment this into lots of sub-images, and then you start to do much better. And then within each sub-image, you will be translational invariant. Not overall, yes. Overall, that's going to be too much, or you will need many, many coefficients. Yes?
For images like the cosmic love one, if you wanted to not just reproduce similar features, but the actual image, could you like fix high density regions, for example, so it looks more like the image?
So you can recover the exact image or an approximation of it. Okay, so if you don't do anything. So in order to come up with a new realization, you need to randomize the phases. So you start to create a new image from scratch. But if you apply the scattering transform to this, you get your coefficients. You can apply the invert transform, and from the coefficients, you go back to the image. And depending on how many layers you use, you will have different levels of accuracy. But it is invertible, so you can go back to the original information. Yeah.
Are there applications to astronomical data sets like the one
Absolutely. So let's go back to the very beginning. All right. So we discussed this 2 days ago. We have lots of cases like this in astronomy where we have very rich data, but it's hard to extract the information because until recently we did not have the right language to do that, the right tools. And so I think now there is a lot to do for images like this. You can think of the ISM, you can think of large-scale structure, all sorts of fields that we see out in the sky, for which the classical moment-based approach, which is very powerful for images like those at the top, but it doesn't take you anywhere for these kind of images. So for those, the scattering transform, I believe, is a very powerful tool to extract the relevant information, the statistical properties of the field. And you can even, once you have done that, you can even regenerate new fields. And that can also be useful for other purposes. There are some ISM papers, very recent. Yes, this is very new. I mean, it's only recently that it's basically percolating into astrophysics. It's been developed by mathematicians for the past, almost 10 years. But I think it's time to start using it. It has great potential. Yes? No, so the main limitation, as I discussed, is that if you apply the version of the scattering transform that I presented today, without the second part carrying dictionaries, okay, so you will do well with realizations like this, but it's not the ideal representation for objects like that. So that's the limitation, okay? Because for objects like that, at some point you do want to have some templates in your network that have cats' faces, people's faces, parts of cars, etc. And the scattering transform will never have that because it's just a cascade of wavelets. So I think it's fantastic for texture. And that's great because really that's the tool that for people like me was missing for so many years. And so especially in physics, we have lots of fields. So I think it's ideal for that, and we should try to explore and push to see, how much we can learn from this transform. Yes.
In terms of implementation of the scattering transform, how tricky does it become, and does it become tricky very quickly as you go deeper?
You need more computational time, but for many examples, people only use the second order scattering transform. There is a fast scattering transform package out there. Yes. But so the message also that I would like you to remember after this is that these convolutional neural nets, they are not black boxes with black magic happening inside. Okay? They basically naturally, when you train them, you naturally end up with an architecture that has these properties built in. Okay, and so the reason why you need convolutions, why you need to do pooling, why you need a nonlinear function in it, why you need different layers, okay, goes basically back to these requirements that we discussed. Okay, so I think to me it's very insightful to learn, to understand where all these properties come from. because that really justifies these architectures that have emerged over the past years.
And then
All
I
right.
think it's a good spot to
Thank
stop.
you.
So let's thank Bruce again.